Welcome back, class. Today we are going to talk about some cool things that have to do with those ellipses that we had talked about earlier. So to give you a little bit of background about the ellipses and specifically how the focal points are significant when graphing an ellipse. Remember that the focal points, there will be two of them, are always going to be located inside the ellipse. So for example, So for example, we would have a focal point here and here. One of the cool things with an ellipse is that if there is a source of light or sound, so say there's a person standing here that is speaking, their sound, or their volume, their voice, will bounce off of the wall of the ellipse, and it will immediately bounce directly back to this second focal point. So no matter where the sound is ejected, so if the person is facing this way and the sound bounces here, it'll still bounce back to this different focal point. A cool thing there is that when we start talking about some actual ellipses in real life, one of the most common ellipses is something called the whispering gallery, and you're going to see one of the problems in your homework tonight about how the statuary hall in the United States Capitol building is actually a whispering gallery. And a long time ago, John Quincy Adams discovered that if he stood and placed his desk at this one focal point, that he could hear all of the conversations of his opponents over here. And it's a pretty big room, so of course nobody would think that he was hearing it. So it's kind of a cool thing. Here's another little way to be able to see how these focal points work. Remember, if you have an object at the one focal point right here, and you bounce it off of the wall of the ellipse, no matter where it hits the wall of the ellipse, it will automatically bounce to that second focal point. So if you watch this little video, it kind of shows you another application of that. So as we can see from that quick little video, by placing the pool ball at one of the focal points, no matter where the person hits that cue ball, as soon as it hits the wall of the elliptical pool table, it's going to immediately go into the other focus point, which is where the hole was. So a couple of applications of this, and I wanted to go back to that whispering gallery. That's actually a pretty common structure. So let's say that we have a whispering gallery, and Jim is standing at one focus and is 6 feet from the nearest wall. Now, excuse me. If we look at this in a diagram, if Jim is at one of the focus points and he's 6 feet from the nearest wall, I'm going to go down to this diagram here. Let's call this Jim, and here's the nearest wall. So the distance from Jim to this wall is 6 feet. Now keep in mind that ellipses are symmetrical, which means if the second focus point is here, then the distance to this wall is also 6 feet. If we go back up to the problem, it tells us that his friend Bob is standing at the other focus point 100 feet away from Jim. So if we come back to our diagram, this focus point is where Bob is standing, and the distance from Jim to Bob is 100 feet. So if we wanted to look at the full width of this elliptical whispering gallery, or this room, from one end of the room, from one wall all the way to the other wall, would have to be 100 feet plus 6 feet plus another 6 feet. In other words, 112 feet. And the first question we're asked is, what is the length of the whispering gallery from one wall to the other? There's that 112 feet. Now, the second question is, how high is the elliptical ceiling at the center? So what we're looking for here is, if this is the center of our graph, I want to know how high is the ceiling. So I'm actually looking for this height. Now, we could start writing an equation, but I would say let's look for some key information about the graph. One thing that we know is that if the total distance from one side to the other side is this 112 feet, if we split that in half, half of 112 is 56. That means that from this center point, wherever this center point might be, From this center point to the other side of the wall, that's 56 feet. From this center point to the other wall is also 56 feet. Now, keep in mind that our focus points are here. Highlight these. Our focus points are here and here. And then we have the ends of the ellipse right here. In an ellipse, when these ends and this focus point all line up, that tells us that these end points are actually our vertices, and that these points up here, these are our co-vertices. Remember, in an ellipse, the focus point will be along the same line, that major axis, as the vertices. So by knowing where those focal points are, that helps us to identify the vertices. The co-vertices then are along that minor axis. So in this case, those co-vertices are up and down. Now remember our variables. The distance from the center point to the vertex. So I'm going to write that down here. The distance from the center to the vertex. That, recall, is our A value. And in this case, that A value then is 56 feet. We also know that the distance from the center point to the focus, so from the center to the focus, that, remember, is our C value. So our C value, remember, here is 50 feet. Okay, now the distance from our center point up to the co-vertices, so from that center up to the co-vertices, that's our B value, and that's the distance that we are trying to figure out. If we already know the A and the C value, we can find the B value by using our equation, A squared minus B squared equals C squared. And our A value was 56, our B value is unknown, and our C value was 50. And then doing a few calculations here, we can come up with, oops, I'm sorry, this is 50 squared. If I do 50 squared minus 56 squared, that gives me negative B squared equals negative 636. Of course, if I divide by negative 1, I have B squared equals 636. And when I take the square root of that, the square root of 636 is approximately 25.22 feet. Now remember, the B value was telling us how far from the center to the co-vertices. Oops, wrote the wrong number there. So that would be 25.22 feet. And that B value is this height that we were looking for on our diagram. So back up to the original question, how high is the elliptical ceiling? This is going to be 25.22 feet tall. So a lot of this is understanding the ellipse and what the A, B, and C value actually mean when we're solving these equations. Okay? A second example, the Whispering Gallery again. Now this is the one at the Museum of Science and Industry. And what we know here is that the Whispering Gallery is 47.3 feet long. Now remember, when we're talking about these Whispering Galleries, we're basically talking about a room that is elliptical in shape. However, it's really only half of an ellipse. So keep that in mind. We're looking at 1/2 of this ellipse. We know that the room itself, so from one end of the room to the other end of the room, is 47.3 feet long. The distance from the center of the room to the focal point is 20.3 feet. So from the center of the room to one of the focal points is 20.3. Now remember, there's 2 focal points and they will be inside the ellipse, which means there's another focal point on the other side, and it's also 20.3 feet. If I want to think about this center point, we know that the full distance from one side to the other is 47.3. If we divide 47.3 in half, I'm going to write that at the bottom, we're going to get 23.65. So what that means is that from the center point all the way to one side of the room is 23.65 feet. From that center point to the other side of the room is also 23.65 feet. Now with this information, think about what we do know. We know that the distance from the center to the vertices was 23.65 feet. That, remember, is our A value. We know that the distance from the center to the focal points is 20.3 feet. That value is our C value. So at this point, we have our A and our C values. First thing here is that I want to write an equation that describes the shape of the room. So my first step is to actually write the equation of this ellipse. Now, because this ellipse is going horizontally, and again, we can tell that it's horizontal because the major axis, which is the one that contains the vertices and the focal points, is horizontal. An ellipse that is horizontal is going to be in the form of x squared over a squared plus y squared over b squared equals 1. And remember, we know that in an ellipse, the a squared is the larger number. If it's going horizontally, then that a squared needs to be under the x. Now, we are assuming, and again, we can do this when we are trying to work these graphs, we're going to be basically positioning this ellipse so that the center is at 0, 0. And this just makes the numbers easier to work with. So if we imagine that this ellipse is centered at 0, 0, then I don't really need to do anything to this x squared and y squared. I can leave it as x minus 0 squared or just x squared. What we need is the a squared and the b squared values. Well, we already know that the a value is 23.65. So if I square 23.65, I can find that my a squared value is 559.3225. The last thing that we need is the b squared. So the first thing we have to do is figure out what is b squared. And again, that goes back to a squared minus b squared equals c squared. I just discovered that my a squared is 559.3225. I'm solving for b squared. My c is 20.3, so if I square 20.3, I end up with 412.09. And as I finish solving this equation, negative b squared equals, if I subtract 559.3225, I get negative 147.2325. Obviously, I want to divide by negative 1 and take the square root. So when I take the square root of 147.2325, I get a b value of 12.13, and we're going to round it to 12.13. Now, let's go back up to question A. Question A was write the equation. The only thing we were missing from the equation at this point was the b squared. If we come back here, we can see that the b squared is this 147.2325. So if I plug in that 147.2325, I now have this equation for the ellipse. The second question was, how high is the room at its center? So now back to my diagram, I'm looking for, from this center point, I want to know the height of the room. I want to know what this value is. Well, remember, if these are the vertices and these are the focal points, then that means this point, these points are the co-vertices. And B, which we've just discovered right here, B is the distance from the center to the co-vertices. Therefore, the height of the room is 12.13 feet, since that was the B value. So again, it really goes back to understanding what your A, B, and C represent and how they are related to each other. Now, another example of these semi-elliptical shapes could be the arch of a bridge. Now, obviously, sometimes these are more parabolic, sometimes these are more semi-elliptical. So in this case, this bridge is in a semi-elliptical arch. The bridge itself has a span of 60 feet. So from one side of the bridge to the other side is 60 feet. We also know that it has a maximum height of 20 feet. So that highest point here is 20 feet. We want to find the height of the arch at a distance 20 feet from the center. So if I looked at this picture from my center, if I went out 20 feet, I want to know how high is the arch at this point. Or if I went 20 feet this direction, how high is the arch at this point? Now, just like we've done with previous problems, I would recommend that we put this on a graph. And once again, we're going to draw this elliptical shape so it's kind of centered in the graph. In other words, I want my center right here at 0, 0. If, remember, the width is 60 feet, then that means that this would have to be 30 feet and the other side would have to be at negative 30 feet. We also know that the height was 20 feet, so that means that this is 20 feet. Now, what I'm asking again is, from this center point, if I go out 20 feet, so if I go out 20 feet, what will be my height at this point? If you think about that in an ordered pair, I'm basically saying if the x value is 20, I want to know what's the y value. Well, the only way we're going to be able to solve for this missing variable is by first writing an equation. So just like we've done with the parabolas, we're going to start by seeing if we can write an equation for this ellipse. Keep in mind some of your values. What we know so far is that the distance from the center to the side is 30 feet. We also know that this is the a value in our equation. We also are given the distance from the center to the co-vertex. That distance is 20 feet, and remember, that's the b value in the equation. So now the ellipse. Since the ellipse is, again, going horizontally, we know that it's going to follow the equation x squared over a squared plus y squared over b squared equals 1. Since we've positioned the center point to be at 0, 0, then we can leave the x squared and y squared alone. All we need to do is replace the a squared with a being 30, so 30 squared, and the b squared, our b value is 20, which means our equation is x squared over 900 plus y squared over 400 equals 1. Once we've got an equation, then in step 2, we can actually use the equation to plug in the value that we are looking for, or the value that we know. And in this case, the value that we know is that x value of 20. So if I take my equation here and plug in that x value of 20, so 20 squared over 900 plus y squared over 400 equals 1. And really, it just becomes a matter of solving this equation. There are fractions. Some people have a little bit more trouble with that. 20 squared is 400 over 900. I'm going to reduce that to 4/9. So now I have 4/9 plus y squared over 400 equals 1. I'm going to subtract 4/9 from each side. And when I subtract 1 minus 4/9, 1 minus 4/9 is actually going to give me 5/9. So now my equation says y squared over 400 equals 5/9. If I multiply both sides by 400, now my equation says y squared equals 2,000 divided by 9. And if I take the square root of 2,000 divided by 9, the square root of 2,000 divided by 9 is a y value of approximately 14.9. So if we go back up to the question, it asked if I go out 20 feet from the center point, how high will I be? And it says that the height will be about 14.9 feet. Now that does seem reasonable since we know that the maximum height was 20. We obviously had to be under that 20 feet still. Okay, last example. This one is a racetrack in the shape of an ellipse. And you can see from our diagram as well as in the writing, we know that the racetrack itself is 100 feet long. We know that the width of this racetrack is 50 feet wide. We want to know what is the width 10 feet from the vertex. So if my vertex point is here and I go in from that vertex, I go in from that vertex point 10 feet. I want to know how wide is it 10 feet from that vertex. So we could look at this picture. We could also replicate this picture on a coordinate grid just to get some numbers to work with a little bit better. If we're positioning this on a coordinate grid, just like we've done in the past, I'm going to put my center here at 0, 0. If the length of the track is 100 feet, then that means this is 50, this is negative 50. If the width of the track is 50 feet, then this is 25, and this down here is negative 25. And what values, think about what values these are here. The distance from the center point to the vertex point, that's my A value. So my A value is 50. The distance from the center point to the co-vertex, that's my B value. So my B value is 25. With these two numbers and the shape of the graph, I could quickly write an equation. Again, since this ellipse is horizontal, we know that the equation will be x squared over a squared plus y squared over b squared equals 1. Since my center is at 0, 0, I don't need to adjust x squared and y squared. All I need to do is plug in my 50 for my a squared, and I'll plug in 25 for my b squared. And so my actual equation is x squared over 2500 plus y squared over 625 equals 1. Now, once we've got the equation, that's step 1. Now we can use the equation to go back and answer this question. If I want to know, if I go from one vertex, and it doesn't matter which vertex, if I go from one vertex and I go in 10 feet, I want to know what is the width at this point. Now keep in mind that, let's go back to this vertex and do the same thing. If I go from that vertex, if I go 10 feet away, I want to know the width of this point. But where am I right here? Remember that it's 0 at the middle, and I went out to 50 feet. So if I back up 10 feet, this is at 40. What I know at this point is that I'm going to be plugging in an x value of 40. So now if I go back to my equation, 40 squared over 2500 plus y squared over 625 equals 1. This is 1600 over 2500. And again, I can reduce that to 16 over 25 plus y squared over 625 equals 1. I'm going to subtract 16/25 from each side. And when I subtract 1 minus 16/25, I'm going to get 9/25. So now my equation says y squared over 625 equals 9/25. I'm going to multiply both sides by 625. So now my equation says y squared equals, now right here I'm actually going to reduce. 25 goes into 625 25 times. 9 times 25 is 225. And now when I do my final step and take the square root of both sides, I get a y value of 15. Go back to the equation though. What is it asking? It's actually asking us for this width from the top to the bottom. What I have found out is that when x is at this 40 feet, my y value would be 15. So in other words, I would have to go up to positive 15 or down to negative 15. So if I'm looking at the actual width, the width from there to there is actually 30 feet. So it is important, once you've established your equation, you've plugged in the value that we are given, it's still important to make sure you go back and answer the question, because the actual question is that it will be a width of 30 feet at that point. So So in your assignment, you're going to see a handful of different ellipse problems similar to these, some dealing with the Whispering Gallery, some dealing with elliptical bridges or arches, and